So one of the big questions from the Roman paper is, where's the fat? Is that why we're not using fat as a fuel as we go at higher and higher intensities? Because the fat just doesn't circulate. So you're not getting a circulation of free fatty acids. You can see the free fatty acid content drops during high intensity exercise. So is the reason that we use less fat as a fuel at high intensity that our muscles just not seeing as much fat? So what they did is 2 years later, they came up with a follow-up study. And all they did in the follow-up study is they infused lipids and they added a little bit of heparin. And what that did is now that increased the amount of fatty acids that are circulating in the blood. So you can see here at rest, when they had control and lipid infusion, they looked at total fat oxidation in the shaded bars, and they looked at the rate of free fatty acid appearance. So how many free fatty acids were circulating in the blood and how much fat you were using as a fuel. So what you can see is that when they infused lipids, they could increase the number of fats that were circulating in the blood. You've increased the amount of fats that are now available to the muscle. So then the question is, when you exercise at a super high intensity, 85% of VO2 max, now what happens to rate of fat oxidation? So we look, rate of fat oxidation, and it's going up, but it's going up minuscule amounts. So it's really, yes, we're getting more fats delivered to the muscle, because when we do the lipid and heparin infusion, you've got now 60 micromole per kilogram per minute versus about 10. So you've increased it almost sixfold how many fats you've got circulating, how many fatty acids the muscle is seeing. But all you've done is maybe increased 5% how much fat you're using as a fuel. So yes, it's important that we deplete free fatty acid circulating, because that's one of the things that happens within our body when we exercise at a high intensity. But that's not what's causing this decrease in fat utilization at high intensities. So this is a paper by Luc van Loon as part of his PhD work. And so what you can see here is that what he said, it was more delivery is not enough. So if you get more fatty acids delivered to the muscle, that's not enough, because what's important is what you can see in this table is he's got workloads of 40, 55, and 75% of maximal intensity. And you can see that glycogen is depleted more at this higher intensity, that you get more lactate produced at the higher intensity. And the important things are these three that I've highlighted in red. PDC, so this is PDH, or the phosphodehydrogenase complex. And the active form of the phosphodehydrogenase complex is PDCA. And what this complex does is it takes pyruvate from the cytosol and it moves it into the mitochondria. And as it does it, it converts it into acetyl-CoA. So the activity of this is basically telling you how much carbohydrate you have coming into the mitochondria to give you acetyl-CoA. And what you can see is at rest, it's at 0.6. You go up with moderate intensity exercise. It goes up a little bit higher as you increase your exercise intensity, and it goes up still higher as you increase your exercise intensity to 75% work. So you've got basically you've got a threefold, a little bit more than threefold increase in the activity of this pyruvate dehydrogenase complex. So you're getting more pyruvate into the mitochondria, and that's giving you more acetyl-CoA from pyruvate. Now what happens on the other side? So remember, fatty acids have to come into the cell. Once they get into the cell, they have to be transported into the mitochondria. And that happens through this transport process called the carnitine palmityl transferase. So this is CPT, or carnitine palmityl transferase, where the fat gets attached to carnitine, brought into the mitochondria, released into the mitochondria, and then the carnitine goes back and grabs another fatty acid. So if you've got free carnitine, that means that you haven't really loaded your fatty acids onto your carnitine yet. If you've got acetylcarnitine, that means that you've gotten the acetylcarnitine into the mitochondria, but it's no longer being broken down. you can see that total carnitine doesn't change with exercise. What happens? Free carnitine goes down. That means that you don't have carnitine on its own. Now it's all bound to acetyls. So these acetyls are the fatty acids. Because as it's going through the CPT, the fatty acid gets attached to carnitine and becomes a fatty acyl carnitine. And you can see that that increases, and that increases about 6-fold during the exercise. And so what's happening is you're transporting fat into the mitochondria, but you're not breaking it down in the beta oxidation cycle. Instead, you seem to be using carbohydrate to give you acetyl-CoA. So it looks like this. We've got acetyl-CoA right here in the middle of our mitochondria. Fats have to come into our muscle. They get converted into a fatty acyl-CoA. They get transported into the mitochondria using CPT1. And that causes it to become a transiently a carnitine acetyl-CoA, fatty acyl CoA, which is attached to a carnitine. And that's right about here. That's not in our picture. Once the carnitine is released and the fatty acid gets into beta oxidation, it goes through that, and that's going to give you acetyl-CoA. And that acetyl-CoA can be broken down in the Krebs cycle or the TCA cycle. If you've got lots of acetyl-CoA coming from pyruvate, because you've got lots of activity of this pyruvate dehydrogenase complex, now what happens is acetyl-CoA is coming from pyruvate. It doesn't need to come from the fatty acids. So this beta oxidation backs up, and then you get acetylcarnitines right here. And so what happens is it's like a traffic jam. You're coming together of two big highways. And one highway here, you're getting preferential access of this highway because the activity of PDH is really high. So all of the cars coming into this area where we've got this breakdown area is coming in, and it's all coming in from the sugar side of the sugar highway, and it's not coming in from the fat highway. And so everything going into the Krebs cycle is coming through sugar because you've increased PDH activity, you've got more acetyl-CoA coming from pyruvate, and now that pyruvate is now going to give you more acetyl-CoA. That's going to cause a backup in the other freeway, in the other highway. And that means that you're going to get a backup on the fatty acid highway, and you're going to end up getting fatty acyl carnitines here that are going to build up and won't let you get this acetyl-CoA buildup coming from fatty acids because you've got more of that coming in from the carbohydrate side. So what's happened is that something has increased the activity of PDH. That means that you're driving carbohydrate in. That means that you're backing up fatty acids. And that means that we're getting more of this Krebs cycle coming in from carbohydrate. And that prevents fatty acid breakdown.